next group of presenters is a large group, and I only have one person's bio to introduce, so I trust that Chris will do a good job of the rest of them. But this presentation is the search intelligence process using artificial intelligence. So Chris Young is the author of the book Intelligent Search, Managing the Intelligence Process in the Search for Missing Persons. Chris has been active in search and rescue since 1981, managed searches since 1986, and is the past reserve captain for the Contra Costa County Sheriff's Search and Rescue Team, and serves as chairman of the Bay Area Search and Rescue Council. Chris is a retired instructor for the Post Direction and Control of the Search Function course for the State of California Office of Emergency Management for 25 years, is currently an instructor trainer for the Managing the Lost Person Incident, as well as Urban Search Management for the National Association of Search and Rescue. And my apologies, this is Dr. Chris Young. Chris recently completed his PhD at the University of Portsmouth, UK, in the School of Criminology and Criminal Justice Center for Missing Persons. So with that, I will hand it over to Chris.
Well, thank you. Now I'm embarrassed, Amy. Thank you. Okay, so it's not just going to be me up here. I got the first 5 seconds, and then I've got this whole front row here, and a couple in the back row here. Some people I want to introduce. That this project is something that started almost 3 years ago now, and through California Polytechnic State University, computer science and software development department. I have with me today Professor Franz Kerfus, who's the instructor that we've been working with this whole time. I also have my partner in crime, Gary Bloom, sorry, Gary, who is, he's the one that originally started this project. It was his idea. And I'll let them introduce themselves as we go along. And we got a whole plethora of students up here. As they come up, they'll introduce themselves, but very briefly. We had to really cut this down to fit it in an hour's time, because otherwise we'd be here all day. So, and we want time for questions. So with that, okay, a quick primer on what is intelligent search. So this process is actually based on a book that I wrote and was published 2 years ago. It's published by Dr. Robert Kester over here in front of us here. Whoops. Got ahead of me. And we're taking the concepts that I wrote in the book, and we're applying that now to, digitizing everything and putting it and using artificial intelligence to help us analyze this. So it's based on, okay, when everybody gets this call out at dark 30, you start heading to the command post. You start thinking about, okay, who are we looking for? We start to paint a picture in our minds of, is this an Alzheimer's walk away? What is it? You start to paint a sketchy picture, and then we start gathering more information, clues, intelligence from interviews, that kind of thing. People have first-hand knowledge of the missing subject. And eventually, we get a clear picture. But in order to really do our jobs right, we really need to start drilling down a little bit more into who is this person. And so if you start getting down to the more granulated part of who this person is, each little pixel here represents a part of this person's life. And, what makes that person unique. And it's up to us to try to put that together, do a better job of looking for them, knowing who we're looking for, what the possibility of scenarios, what's going to happen. And that's how this all works. And it takes a lot of energy to do that. And so we're putting this together now to help the computer and artificial intelligence help us get through that process. Come on. It's not working. Gary? Yes, technology, actually, yeah. And I don't want to hear any comments about Mac computers. One moment, please. Okay, here we go. Okay, so what is intelligence? Okay, I quote from Sherlock Holmes. Data, 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 he cried impatiently. I can't make bricks without clay. You can't do our job without enough information to figure out where to look, what to look for, what are the circumstances, and what's going to happen, or predict what's going to happen. Okay, it's actually a circle process where it starts with plans and direction. Somebody at the beginning sets, okay, here's what we're going to do. In the military, which is where this came from, it's okay, we got to move troops from here to there. We got to defend ourselves or do an offensive. They start collecting information, processing that information, analyzing it, and then putting it into something that we can hand up to the commander. That's something that's actionable, something that they can do with. Okay, we could send it to plans. They write an assignment, and off they go. That's the process. So the first parts of it, the collection, the setting the direction, that's pretty in most search and rescue, incidents. That's pretty well set. But in the collection of information, that starts with the person calling up and say, "I can't find my missing father or my daughter or whatever." So the next part, the stuff in yellow, is what we normally do by hand. We start, writing things up, filling out forms, getting that, processing and exploitation and analyzing and production, which is a lot done up here based on personal experiences of those that are actually managing the searches. And the more experiences you have, the more you better you are at it. The rest of it can be done electronically as well. I think this is where I pass it on. Is that right? So I'm going to pass this on to Gary Bloom.
Hi, thanks, Chris. So good afternoon. I'm Gary Bloom. I'm a longtime member of San Mateo County Search and Rescue. I also have a fire background, but my core function was I was a software CEO. So I'm a tech guy, a Cal Poly grad. This project actually started at Cal Poly, and it was an idea I had that said, I'm pretty frustrated with the paper-based system that we manage searches on, and having run some really large searches with 200 to 300 people in mutual aid, the paper system just stacks up, becomes very difficult. And I had this view and this vision that says, hey, we could do this differently. And so that's what's the beginning of the project. I went to Cal Poly, where I'd graduated from, where I'd been involved, and we started it as a student-led project along with a sponsoring professor as well. And Cal Poly, for those of you who don't know, is a technical institution. It's a California State University, extremely highly rated, and it has a motto of hands-on learning. And so what better way to learn than to go build a system to solve a real-world problem? And that's what we set out to do. So the project overview, collaborative effort. Chris came along, got Chris involved, which was a nice addition to it, add another search and rescue mindset to it. And we started formulating more and more of what we could do. And this all started in 2021, and it sounds like a long time ago, and it is, but remember, it's a student-led effort to the most part, so we have a lot of turnover on almost an annual basis. But we've got the system in a really nice place, and a place that we can actually start showing you. So the vision we have is, it's a little bit of the art of what's possible. If we are collecting the data in real time electronically, then we can start applying AI to it while we're collecting the data. And that's the ultimate for me. That was the holy grail. It wasn't just, can I take all these forms and kind of modify them to be electronic? I could do that with PDF. It was the idea that says, no, let's put a system behind it where we're actually collecting, processing the data, and applying intelligence to the data based on lots of things we already know out in the world, so that we can locate the missing subject. And ultimately, if you want to simplify it, what it's really all about is find the missing subject faster, because it also takes a lot of time, because for those of you that have managed large searches, you know that information doesn't flow smoothly. I can reflect on some experiences I've had where it's at night that I'm reading all the debriefing forms, and I find a really important clue that would have been nice to know about 8 hours before. And that's the information not flowing very well. So the idea here is, well, let's put a system in place that we can find people more quickly. The reality, though, is that in today's world, SAR is predominantly a paper-based system. I have not found in my travels and looking and doing lots of mutual aid work, I haven't found anything other than a paper-based system. It's really everything from check-in to the completion of the search and writing the final reports has all been paper-based. So that reality actually makes it really difficult. How do I analyze data that's on paper? And so what are we aiming to do is we're trying to take this big stack of papers, and instead, step one is let's get all this into a database and let's automate the entire search management process. All of the forms, all of the ICS forms, let's put that data in a database in real time. It's going to improve productivity. Just this step alone will improve productivity because of the flow of information. You'll see a demo of where the system is. You get a flavor of how information flows. But then ultimately, if I'm collecting it in real time, then I can link it into AI models and I can start predicting where I'm going to find the individual. And that's kind of the art of what's possible with this system. The second thing we have to do is whatever data we're collecting in real time, we have to enrich the data with other data sources. We've had a really great partnership with Dr. Kester, have made a lot of use of his data, which gave us a foundational set of data to start building out AI models. There are other public data sets out in New York, a Yosemite data set, and then you have all the mapping data, mapping technology that most of you are familiar with. The second or the third step then, I have it in a database. I'm now enriching the data that I'm collecting and the data that's already been collected. The third step is let's apply AI to the enriched data to improve the search outcomes. And where we're at right now in step one of the process is it all starts with real-time data collection, where we're basically automating the search. And rather than talk about it, I'm going to ask Julian to come up, which is one of our dedicated students. And Julian is going to give you a quick walkthrough of what the online system looks like. This part of it's actually largely complete, so we can actually show you what the system looks like and give you a taste of it. Julian?
All righty. So I'm Julian, and I'm going to give you a quick demonstration of our platform. And to do that, we're going to run through a hypothetical search incident of a kayaker who got lost during an outing in the Baltimore Harbor. And we're going to see how we would use the platform to enter and then pull data back out during an incident like that. So the first thing we need to do is actually create the incident in our system. And so you can see we're on the home screen here. We will click on the blue Create New Incident button, and then we'll start filling out some preliminary incident information. And so whoever arrives to the command post first could take a few minutes. They could do this, and then they'll simply click the Submit to Command Post button, and the incident will be created and entered into the database, and then we will be ready for more data collection. So you can see we'll click Submit, and that will take us back to the home page. This page displays a list of all the currently active incidents. And so let's navigate to the one that we just created. We'll click on it, and this will take us to our incident dashboard. And the dashboard is going to be a way to aggregate data and display some very useful information based on what's been collected so far. So unsurprisingly, it's looking fairly empty right now, and that's because we haven't actually collected any data yet. But let's start with that. So the first thing we need to do is create our briefing. So we'll use the top bar to navigate to the form, check-in and briefing tab. We'll click on our briefing form, and we'll start filling this out. And the beauty of doing a briefing like this online is that in the historical paper-based version, the briefing would actually have to be physically printed out and distributed to the searchers. But using our online system, we can now have them log in. They'll be able to open up the briefing, and they'll be able to see all of the latest briefing information. So as things change, as things are updated, we won't need to reprint forms. We can simply have them log in. And as we'll see here, they'll navigate to the All Submitted Forms tab, and they'll be able to see the briefing, click on it, and they'll get all of the most up-to-date information. All right, so the next thing we're going to do is we're going to create an agency check-in list. And so again, we're going to navigate to the check-in and briefing tab. We're going to click on this, and we're going to start filling this out as well. And so what are some advantages of having information like this in a database? Well, for one, we can store things like timestamps. which if the incident turns into a criminal investigation, information like that is going to be crucial for law enforcement. So we can store things like when a form was created, when it was edited, and when it was accessed. And then another really nice thing we can do is we can pull the data back out of the database. We can display it on the dashboard, and that will give our command post staff a really nice overview of the kind of resources and the kind of information that they have available during the search. And so what we'll see in just a second here as we click submit is that we now have in the bottom left corner the agency that we just entered, and we have a head count of the total personnel who are signed in from this agency. And so as the search progresses, we can see here we have another agency that just showed up. We have some more personnel that signed in from our original one. And we now have our third agency that just arrived. And so you can see how the dashboard creates a very nice flow of information to the command post staff without having to sort through and look through physical paper forms. All right, so let's actually use some of these resources and make an assignment. So here's our team assignment form. As you can see, we've assigned for 2 divers to go diving in the harbor, and they're going to go searching for clues. So we would fill this form out, we would submit it into the platform, and then the divers would be able to open this on their own device, and they would be able to see the assignment, go out, complete it, and then as they're coming back, they'll need to fill out a debriefing form. So you can see here we have our list of debriefing forms for the different types of teams. And just to keep things simple, let's use the general debriefing form, which as you can see here, the dive team has come back. They've filled this form out on one of their devices. And if we look at the bottom at these highlighted areas, we can see that they found a couple of clues. They found an orange shoe and they found a piece of plastic. And so let's have them enter these clues into a clue log, which we can see right here. We have our clue log, and we can see we have both of the clues entered. We have time, date, and coordinates of the clue. And what we'll see in just a second here is as we submit this form, our dashboard is going to update in real time. And we can now see we have our 2 clues on the map pane in the upper right-hand corner as these little icons. We can click on them on the map to get location-based information. And we also have this nice clue pane just to the left of the map, displaying all of the clues that have currently been entered. And we can also sort this by several different parameters. And so compared to the historical paper-based approach, this is very nice. Instead of someone having to look at the physical clue logs to know when a clue has been logged and submitted, we can have them log in. They'll open immediately to the dashboard, and they'll be able to see these clues appear on both the map and the clue pane. So it's this very nice, quick, and efficient flow of information where we're eliminating the time lag of person-to-person and form-to-person communication. Okay, so this is all we're going to see for the demo today. We didn't have time to show it, but we also have the missing person questionnaire, which is a form that has 2 versions. There's a short and there's a long version. And we actually also have both of those implemented in our system. All right, so I'm going to talk briefly about the technology of our platform. So we designed it to support different devices. We understand that there'll be users both in the field and in the command post using this platform. And so it's usable on desktop, phone, laptop, tablet, whatever you have. As well as the system is implemented on top of a Google Cloud infrastructure. And so one really nice thing that lets us do is store data locally on a user's device. And this is great because we understand that not everyone will have access to a cellular connection or an internet connection while they're using this platform. So what we can actually do is store data locally on their device when they're out of service. And then when they come back into a connection, we can sync that back up with the cloud database. All right, so as far as our status, you could see that we had the forms are all submitted and they're ready for field testing. We have our database schema complete, and we have some basic data validation going on. Also, behind the scenes, we have a search engine that's been integrated into our database, and that's almost ready for integration into the interface. As you saw during the demo, our dashboard was largely complete, and we had data coming out of the database and being displayed on the dashboard, as you would expect. And then the very last thing, and this is an ongoing piece of the project, is we're trying to redesign the user interface to make this an easier to use platform. So as you can see here, this is a prototype for our new user interface. We've moved the navigation from the top to the side, And there are also a couple of other changes that we feel will make the platform easier to use and easier to learn for people who want to get started with it. So that's all I have for you today, and I would like to invite our sponsoring professor, Dr. Franz Kerfess.
Thanks. Okay, so I could, of course, talk forever about artificial intelligence and how we could use artificial intelligence in this context here. But considering that we only have limited time, I'll keep this very brief. So we will have 4 different types of technologies that we're going to talk about. There are plenty more, but these are the ones that we already looked at or that we're currently actively investigating. So semantic web is a technology that was invented about 20 years ago. It was popular in the 2000s. Now it's not really so popular anymore, but there are still some valuable lessons, tools, and technologies that we can use, and especially so-called ontologies. We'll come back to that in just a minute. Then we'll talk about decision trees and machine learning. Decision trees have been around kind of forever in terms of artificial intelligence since the 70s, 80s. They're still useful tools. They're relatively easy to construct, and they are also very helpful. Machine learning also has been around for a long time, and what we are using are some of the kind of old-fashioned machine learning technologies that you'll hear about in one of the student presentations. Then one of the more recent developments in artificial intelligence is called deep learning. So that's machine learning on steroids. You use a lot more data, you use a lot more computing power, and you also have some refined methods that work better with all of these data and the computing power. And then finally, we try to bring all of this together into hybrid systems that utilize all of these technologies and try to bring them together. So you can see a sample of tools that are currently popular in the AI community. Don't bother trying to decipher all of them because it changes on a weekly basis or so. The ones that we are actually using are the Google Firebase that you already heard mentioned in Julian's presentation. Then for semantic search, we use the Algolia search engine. So semantic search is basically similarity-based search. If you have a clue where somebody says, okay, we found an orange Nike shoe, but the person reported missing was wearing a reddish shoe. If you do a database lookup, then you won't find a match. If you do semantic search, then the semantic search engine will say, oh, reddish, that is kind of similar to orange. Maybe there's a match there. Then we have semantic web technology, so I'll talk about that in a couple of minutes. We'll also have machine learning and deep learning, and the tools that we're using are pretty much standard tools in the AI community: PyTorch, scikit-learn, Keras, TensorFlow, maybe a few others that my team used that they didn't tell me about because things change so quickly, but they will also give you a little bit of that. And then we're using the latest development, generative AI, large language models. When we started this project, large language models were not really on the scene. They existed, but nobody really used them to the degree that we use them now. So this is a quick look at the technologies, and here is an overview of our system. If you start from the left, we have an experienced search manager at the command post. They type in a query. The so-called query intent engine tries to figure out what are they actually asking for. And in a conventional search engine, you go to that cloudy thing at the bottom, and the search engine will give you a set of links that hopefully will answer your question. What we are trying to do is to augment this query by incorporating semantic knowledge. And this semantic knowledge comes from a so-called ontology that describes in a systematic manner the domain, the area of knowledge that we are interested in. This area of knowledge utilizes the current search information. It also uses historic search data, for example, the ISRID data set. It also may have access to external services, map and temperature and other related data. And it uses natural language processing, so basically the large language models, to bring all of this together and bring together the different search aspects and the different missing person aspects into one coherent image that then answers that query that the search manager has in a much better way. So that's the overview of our system. And here's a quick look at the semantic web technology. So it uses a so-called ontology as a backbone of a knowledge repository. So essentially a database, a knowledge base. And we use knowledge retrieval and reasoning technologies to look at a collection of these digital documents, both historic as well as current, and try to make sense out of it and give back information to the search manager that helps them. This is the basic core of old-fashioned expert-based system technology, where we try to capture knowledge that humans have and explicitly represent it in computer technology. This has been around for about 50 years. It's still in use. It's not as visible as it used to be, but there's still value in using that. On the left, you see the tree of life that many of you may be familiar with. That's one way of trying to structure an area of knowledge in a hierarchical manner. It's also referred to as a taxonomy. An ontology, again, is a taxonomy on steroids where you have a lot more information in there. And this ontology is the framework that we use to capture our knowledge. But the problem with ontologies and related technologies is that they are very labor intensive and very expensive to construct. So all the efforts that people have put in there are not really practical in our context. It is still useful for what we're doing, but not as useful as people initially thought it would be. What we're also experimenting with is to extract knowledge graphs from text. So we have text-based documents. We use large language models to browse through them, identify interesting bits and pieces, and represent them in a graph data structure that is amenable to computer treatment. And this could be used to construct something like this here. I call this an IntelliSer glue graph, where you have connected pieces of information that can point out interesting insights into the search process. So the orange dots, for example, could be people involved, the missing person, as well as rescuers, as well as friends, and so on. The blue pieces could be clues. The green pieces could be location data, and the purple ones could be other pieces of information that are possibly related or not. And we could also do a geospatial analysis in various forms here, so we can look into this information and try to find point-to-point connections. Where was the person last seen? What was the goal they were trying to reach? And what are the possible routes that they could have taken? Then the coverage area. Who is currently out there looking for the missing person and what areas can they cover? And then also something like what's in this image called fleet optimization. I would call it resource optimization, where can we deploy the resources that we have at hand. And at this point, I'm going to hand over to our team of students. And the first presentation will be by Vasant Pugalenti about decision trees and machine learning. So, Vasant.
Hi, everyone. I'm Vasant Pugalenti, and then I'm going to talk about what the machine learning team has been doing. So the goal of the machine learning team is to train the machine learning models on various search and rescue data sets that we have to predict, reduce, and analyze the cost, resources, and time that goes into all these search and rescue missions. And we hope by doing this, we can enhance the efficiency of search and rescue missions by directing searchers to high probability areas of where these missing people might be. And then connecting back to the panel, I remember someone was talking about how the phone pinging might not be the best way to find out where a missing person might be, but it's actually a factor of many information that comes together. And that's exactly what the machine learning team is trying to do. And this approach will reduce both the time and financial costs that come with the search efforts. And so the data sets we're using are the ones you guys are familiar with. ISR2 and ISR3 are our most prominent data sets that we use in our training. And it has close to over 62,000 observations and has a lot of broad categories and more precise details like latitude as well. And let me show you some stuff we've been working on. So some of the pattern recognition models we have include k-nearest neighbors. So this pattern recognition model looks for cluster patterns in the data sets and tries to uncover similarities between different categories of missing people. And some categories it can differ by is age, weather, which also connects back to the panel of how weather can be an important factor, and also health conditions, and much, much more. And here's some findings we have found through ISRA2 dataset. So with the relationship between the age, group size, and wandering behavior of a missing person, we found the following relationship. So we found that individuals aged 75 to 85 in groups of 1 to 3 show a higher tendency to wander, which is consistent with previous dementia related findings. And as you can see in the graph, the pink side is the people who stayed put, and the blue color is people who wandered. And then the x-axis is number of people in the group, and the y-axis is the age. And as you can see, the people in the older section tend to wander, and also people in the very young section also tend to wander. And another finding we found is a relationship between age, incident time, and gender. So as you can see in the graph, we have the incident time on the x-axis and age on the y-axis, with male being blue and female being pink. And we found that older males tend to get lost more at night, and with also females getting lost between also later at night, but at a younger age. And I'm also going to invite Jerry to talk about K prototypes clustering. He's part of the ML team, and this is something he's been working on.
Hey everyone, so K-prototypes clustering is another way to model cluster data prototypes. And this way, there's different types of clustering: K-means, K-mode, and K-prototypes. Prototypes means it could process both categorical and numerical data, which in this case that we'll be using total hours lost, which is numerical, and area type, which is categorical. And so when you group by total hours lost and area type, you could see that like for even in every area type, you could clearly see the differences in the time it takes for people to get lost. Like cluster 3, the blue one, it's really small, tight, around 0 to 100 hours. And then like cluster 2, the orange one, probably around 200 to like 350. And these types of models are really useful in just representing the data, and you could visually see the patterns that appear, and it'll help you process the data more easily.
Thank you. And another model we have also been working on is support vector machine regression. So what this model does is finds the best fitting line between the data features that we have included and puts it in the most efficient way. And this uncovers trends between categories of missing people, which is similar to the previous models I've talked about. And some findings we found here is a relationship between age and the time this person was lost. And that's the graph which shows the age with the best line fit. And we found that individuals aged 50 to 60 specifically show a tendency to be lost for longer periods of time compared to other people their age. And overall, with the machine learning team, we hope to integrate this with the front end, as you saw earlier, where the front end is able to add missing person reports instantly. And we hope that as they do that, we can also predict where the person might be based off the following input features that was talked about earlier. And it can be run through the models. We can give high prediction accuracies. And then hopefully by doing this, we can reduce the time and resources required to fund and then complete these rescue missions. Thank you. And now I'll hand off to the probabilistic reasoning team.
Hi everyone, I'm Amanda, and I'm going to be talking to you about probabilistic reasoning, which is a type of machine learning. It's also based in statistics. So what is probabilistic reasoning? This is the use of probability and logic to deal with uncertain situations. So this is something you guys do all the time. You get some sort of basic information about your missing person, you make some sort of educated guess about where they might be, what you want to search for, and then maybe you find more evidence and you update your guess or your search decisions to better reflect what evidence you have and where you're going to search next. So what we want to do with this type of model is take your human experience of how you conduct searches and make it into something computer-based. So these are some factors that you might have in a missing person search. Situations, so are they missing? Are they injured? Are they a fugitive? Something like that. And then response type, are you doing a search or a rescue mission? So we're representing this as a Bayesian network model. So this is a graph you might see from that. And we see this arrow connecting situation between response type. That means there's some sort of association between the situation and how you do the response or how you do the search. In statistics, we know that association does not mean causation. So we don't know that the situation type is causing you to do some sort of search or rescue. But you guys would know that if someone's injured, say, you're going to do a rescue and not a search. So in statistics, we have this idea of causal inference. So how can we determine if there's causation between two different factors? We can also find hidden or underlying causal relationships that weren't shown in the graph. So here's an example of a Bayesian network. We see the situation and response type that we saw before, and we also see two other factors: activity, were they camping, hunting, hiking, something like that, and found in search area. Did you find the person in the search area or not? So we see that there's this association between situation and all three of these factors. But what if we actually find out that there's underlying relationships? So maybe that activity is also influencing whether someone's found in the search area. So why is this important? How could you use this? Normally, causation can only be determined using an experiment. So you might say, we tried to find a missing person with 5 rangers. Then you tried searching for a similar missing person with 5 rangers and 1 dog. And you come to the conclusion that using a dog causes us to find a missing person 2 hours faster. But experiments are expensive, or they could risk someone's life if you do it in a real-time scenario. So what if we use causal inference to do this based on historical data? So from the last decade of data, for similar missions, if we increase the number of dogs by 1, there's a 2-hour decrease in search time. So we come to the same conclusion: using a dog causes us to find the missing person 2 hours faster. But we were able to do that without risking lives by doing an experiment in the field or by using up a lot of resources making a simulated mission. So obviously you guys know that using a dog can help find a missing person faster. But there are hundreds, thousands of factors that affect these missions, and the human brain really cannot process all of these different associations between these factors. But a computer can do it with a press of a button really quickly. So this is why we're using a Bayesian network to try to find these associations, and that might be able to reduce mission times or decrease the number of casualties. And then next, we're going to look at deep learning.
Hi guys, my name is Brandon, and Charles is coming up to the stage with me. That is Charles right there. We are part of the DL for Search and Rescue at Cal Poly. All right. So what is our goal of DL for SNR? So our goal is to utilize deep learning methodologies to predict where a person can be found by creating a probabilistic heat map given an operative description. So as you can see on the board right there, that's kind of like what our output should look like. And this type of model that we're utilizing does involve a lot of different types of math and algorithmic science. But for now, but we'll explain more about it later. But for now, and if you don't want to get too technical, just think about this like deep learning methodology as like a black box, a mysterious, hungry black box that like kind of feeds on a lot of different types of data. And once it's done consuming the data, the black box is able to learn it, to understand and interpret an operative's English clues, like just natural language clues, into a probabilistic heat map to determine where a person can be found.
Yeah, our objective is to create what's called the multimodal neural network. Is there another microphone? Okay, I guess we will trade. So as I was saying, at the end of the day, our goal is to produce what's called a multimodal neural network to do what I like to call lost person location predicting. More on that later.
So through our model, we aim to learn from previous cases and achieve a more accurate initial search point. This is really important when it comes to search and rescue, especially considering that search and rescue personnel and resources are finite. There's no infinite resource, and being as efficient and effective as possible will definitely be super beneficial to all of you guys. And our goal mainly is just to assist with search and rescue and be able to determine the most accurate as possible to starting point.
So yeah, back to the whole multimodal thing I was talking about previously. So what does that mean exactly? It means our model consumes 3 kinds of data. Modalities in a human sense are like seeing and hearing, different sensory inputs. Well, to our model, they are images and then natural language. If any of you have ever worked with ChatGPT, I know that's a very popular language model these days. We employ a very similar architecture with our model, SARformer, as shown there. We consider the intersection of a language model, a computer vision model, and then as well as the tabular circle there. That just indicates that some of the data that our model consumes remains in a table and isn't as free-flowing, so to speak, as natural language and as images are generally. So yeah, this diagram outlines our model. On the left-hand side are what we call the encoders. They transform the data into an abstract representation. This abstract representation is non-human interpretable. It's a very interesting aspect of deep learning. It's, as Brandon was saying, a black box. And then on the right-hand side, our model, represented by the large trapezoid there, consumes the abstract representation and then transforms it into what we call a probability map. Then the probability map would be overlaid with a real map, and then it would give its users its best guess as to the exact location that it thinks the lost individual would be. Where, just for explanation's sake, the highlight tones there correspond with likelihoods. So the darker regions would be the model's best guess as to where a lost person would be within this region. And so, yeah, if you'll allow me to wade into the weeds very quickly, our model uses what's called supervised learning. That is to say, it makes a guess and then compares its guess to a ground truth example in the data. So if we have a data point, like where each column represents maybe a different clue or different aspects of data that it's consuming, or with the specific example of ISRID, various features, number of people lost, height, etc. It consumes those and then makes its output and then compares its output with the exact point that the individual was found lost, and then updates itself in an iterative process to make better predictions over time. It's sort of similar to how humans gain more experience through just coming into contact with more search and rescue operations, right? Similar idea.
So in conclusion, the variation and the scale of the data that we're able to get really highly correlates with how powerful our model then is going to be, especially considering our multimodal nature of our model, the fact that a lot of these different factors that can go into a variety of different cases, like the case-to-case variation when it comes to the different factors that go into it, will definitely benefit our model's performance at the very end.
So yeah, our approach is what we would like to call the most theoretical, and in that way, it's a bit of a moonshot. If it works well, we hope it can be a powerful new tool, but there's no guarantee. So I guess that's it from us.
And now we'll hand it to Dr. Kerfus.
Thanks, Brandon. Okay, so this was a quick look at some of the work that the students have been doing over the last year or so. If you want to find out more about it, we also engaged in a bit of a stealth operation and put up some posters over there where the donuts used to be. So if you're looking for donuts, go over there. If you're looking for more information, also go over there. So our hybrid systems approach is basically to take a lot of this information and use the predictions and the insights that our system can collect based on one hand, the current ongoing data from the search, the clues, as well as the historical data that we know from databases and collections like Bob Köster's, use that to guide the activities that are going on in a current search. What we're not trying to do is to replace people like yourselves with artificial intelligence. In my opinion, that's a hopeless enterprise because there's so much out there that humans know about that never can be captured by artificial intelligence. On the other hand, for me, as an outsider who doesn't really know much about search and rescue, it's pretty clear that there's a lot of data out there, a lot of information, a lot of knowledge that gets lost because it's not there at the right time, in the right format, or in the right person. Because a lot of you are also probably close to me, close to retirement age, and who's going to keep that knowledge around? So what we're trying to do is to collect as much information and knowledge as we can, utilize computing technologies to improve the efficiency and effectiveness of search operations, and bring this back to those of you who are actually doing the work of performing such search. There are, of course, also some practical aspects of exploring these artificial intelligence approaches. One of them is that there's a lot of stuff out there, lots of technologies, lots of tools, lots of developments. What we fortunately are in a position in with our talented and highly motivated students is to experiment. If you do this in a commercial enterprise, then you can't afford to do this. We can do it because our students work for almost free. We pay them, but not really enough. I see it as an investment in your future career. And of course, some of them also get benefits out of it, like Amanda, she's working on her master's thesis. A few of the students are working on senior projects or on similar activities. Another problem that we have is also the use of computing facilities. Some of the work that we're doing challenges the computing facilities that we have available at Cal Poly, and we're looking at opportunities to reach out and find high-performance computing access. And fortunately, we already have some connections, but there's always a demand for more computing power. Right, Charles? Right, Amir? Yeah, please. Okay. So then for the conclusions, I'm handing it back to Chris. Okay, Chris, you're doing the conclusions.
So I'm not going to go over, you guys can read all that. I'm not going to go over all the detail, but as you can see, we've been working diligently for almost 3 years now, and we've accomplished a lot. There's still more to do. Everybody that's sitting in the front row here it's been a pleasure working with them and watching little lights go off in their heads and going, oh, let's try this approach. Let's try that approach. And it's been doing that again for, multiple different students. I mean, this is just the tip of the iceberg, so to speak. So what we're really looking for towards the end here, though, is we're looking for a partner to help us kind of, I hate to use the term commercialize it, but that's really what we're trying to do. We've done proof of concept. It's like what we call a seed project in academia, and it's ready to take it to the next step. And so we're looking for partners on that. And if you know of any or you're interested and have some money or whatever, well, we're looking around too. We've got other potential possibilities, but that's where we're at right now. And so with that, I'll open it up for questions. Yes, sir. Okay.
Chris, I've got Ken Chia and I have been going back and forth a little bit. He kind of wonders, in this Google Firebase database, did you guys do like an import of the ISRA data? Or are you scraping the data from somewhere else? Are you accessing it directly, like through an API? We're just kind of curious, I guess.
Okay. You got to come up here. There's a camera on you.
Hey everyone, I'm Jerry. I'm the backend league on this team. But for Google Firebase, it's mainly just a storage for using the AI for SAR like website. We have stored all our data in terms of like machine learning, that stuff separately. But the Firebase is usually just for like real-time data that we want to like see how we want to use. So I hope that clears that up.
So the other half of the question is, are we taking bits and pieces, scraping the internet and stuff like that, which is what ChatGPT does. You ask it a question and it goes out and searches whatever data is posted on the internet out there. And we've actually been using data that's within the system itself. It's kind of like a closed system in parts. It's not that we're not using ChatGPT. But the other thing is that Dr. Kester was kind enough we made an agreement with him that he would lend us his database, and we are in the process of helping him clean it. So it's a synergistic relationship, I think, here. And we are eternally grateful to you, Bob, for all that. And I mean, it's been interesting. They've been having phone calls back and forth between the students and Bob, and just, okay, what does this mean? What are you trying to do here? And just cleaning little pieces up, and it's been very helpful. So we're all gaining from that. So I hope that answered the question. That was sure.
Yeah, I'll just add, I just want to make sure it's real clear. So the demonstration you saw from Julian, which was a recorded demo in PowerPoint of the actual core system, that's the part that's currently using Firebase. And what brought us to that was a cloud infrastructure that allowed us to have somebody else manage the physical environment for us. But the front end of that had persistence so that on a mobile device, I can be collecting data, even if I'm not connected, and then have it synchronize. So that part of the system, which is the core web system, that is largely functionally complete. I actually had it out at a search and rescue training I was at yesterday, Saturday, I guess it was Saturday. I got partway through entering some of the data in the system. We had pretty weak Wi-Fi connectivity, but I was able to get data entered. What really chased me away was the incredible amount of rain we had in Northern California and the lack of adequate tent space to hide under with my laptop while everybody else was trying to do a massive mock search with about 60 people. But otherwise, that part of the system is largely functionally complete. Then when it came to the different AI projects, they're using the data sets in all kinds of different technologies that allow us to apply the AI to it.
So I've got two more comments online, and then we'll go back to the room. Charles Torty says, very happy to see an ambitious multi-year research project on predictive models for lost person behavior and an exploration of multiple methods, and +1 for Bayes nets. I know it can take a lot of tuning, but do you have any measures versus base models like ring or bets?
Yeah, everybody's looking at each other here. Yeah, spell it.
Ring is R-I-N-G, or bets. I don't know. Charles, can you elaborate? And you can come off mute if you want.
Can you hear a voice?
Oh, hi. Sorry, I meant, have you had a chance yet to compare to the ring model distance from IPP? Or if not, because these things take time, do you have internal bets about the different approaches?
Somebody want to take that one? Can you repeat the question one more time? We got to turn the volume up here so we can hear it.
Yeah, in the different machine learning approaches, have you had a chance yet to compare them to some of the non-AI models, like the distance from IPP ring model? And if you haven't had a chance yet, do you have internal bets about the different approaches that you're trying?
Come on, Charles. And I'm assuming he's talking about the probabilistic rings. But go ahead.
So at least on the deep learning side, we have not had the opportunity to make that comparison just yet. We fully intend to compare against pre-existing methods for doing what we're doing. Our model is a little bit more granular in that instead of rings, we could produce effectively any region, and the region could fit any environment. It's not just, we think that the person is within some circle that has like a 5-kilometer radius or whatever. We could be as granular or as sort of abstract as the data deems necessary.
Yeah, Charles is at a little bit of a disadvantage on this, not understanding the concept of the rings that we all use as to, determining the proximity of where somebody's going to be found. But you would have seen some of that work in the charts that we're showing as an example where, older males my age in a group tend to wander. Hopefully I don't have dementia, so I'm not one of those. But you can start seeing some of that analysis. There wouldn't really be anything holding us back from doing that kind of ring analysis that we use in search and rescue today to try to predict how far from the point last seen the person will be found. But we haven't actually applied that direct technology or applied our technology to that exact problem as of yet.
Thank you.
From Quentin, where can I find more information? Is the system open source?
Well, that goes to my next slide.
All right.
Except the video picture's hiding my QR code. This is my contact information. I'm the point of contact right here. If you could see, there you go. That whole QR code, if you put your camera on that, it'll actually come up with a contact for with my contact for your cell phone. That's really the best answer we can give them. Yeah, go ahead, Gary.
All right. And
I'll give you the last part of that. It's the short answer is no, we haven't officially open sourced it, but we also don't have any particular pride of ownership. We're looking for partners or people that actually want to be involved in the technology and take advantage of it. So no resistance there. The one part of the resistance we have is we do have Dr. Kester's data, and we have agreements to protect that information. So we have to be mindful of the agreements that have given us access to a wealth of knowledge, and make sure that we don't expose, kind of that set of data. But otherwise, no particular pride of ownership. If you're interested, just reach out. We can talk to you about which piece you might want a copy of or to take. And we're not, like I said, we're not no particular pride of ownership. The mission here is use technology to help out search and rescue. My goal of starting the project when I did was pretty simple. Is I thought this was all possible. We've now proven it's possible, and now I want to see it actually help find people quicker.
from Ed to the deep learning team, are you able to interrogate the processing to find which adapted segments are having the most influence on predictions?
Once again.
Good to know we have some technicians on.
Yes, so ultimately one of our goals will be to do just that. Perhaps to summarize for those who are unfamiliar, what I believe they're referring to is sort of adjusting small parts of the input and seeing how that changes the output. So for example, instead of 2 men, maybe it's a woman, how does that affect the ultimate location where our model thinks the individual is lost? I guess if that isn't how they meant it, please clarify.
And then before I hand the microphone off to Amy for questions in the room, this is from Ken Chia, would we even be thinking of rings, dispersion angle, etc., when the AI is finalized? It might recreate rings in its output, or it might not, but isn't starting from any particular model, only drawing directly from the data to create a heat map.
I'm confused as
the hope is that they match. I mean, yeah, I mean, that's.
I can speak with respect to that. So our model, we give our model the freedom to produce any shape that it so desires, right? And so if it were just simply constrained to rings, that's what if a ring doesn't fit the situation, right? So yes.
I'll just very briefly add to it. I mean, the goal isn't really to create a ring. I just want to remind everybody what the goal is. The goal is to suggest to you as a search manager where the likely place is you're going to find the individual. And that's what we're trying to do. We're collecting the data in real time. We can match the real-time search that's going into that Firebase system. And we can match that data against these AI models that hopefully say, I really should be looking over there, not over here, at least from a computer's view. Again, not replacing the human view, which also has experience.
And there's one other part of this as well, which is the type of data that we're collecting, like if you're interviewing someone, that information as it's being, that you ask them about, okay, are they an active hiker? Yes. Okay, that gets put in the database like right now. And then that gets adds it all up. And then we were hoping, again, what this is going to be doing is that as you're asking questions, it'll pop up on a little screen saying, okay, have you considered asking this question? Or the responses that you're getting will lead you in a direction to be able to say, okay, maybe there's something else we're not thinking about. There may be something part of this. And the other thing that this is for, it's not just for us, old timers that have been out there since year one, but it's for those that are up and coming. To give them a tool and the institutional knowledge that we're collecting from all of you out there ourselves to be able to apply that to the next search. And, it's what Bob's been doing for years is lost person behavior. It's the same idea. It's the collective knowledge. So how can we be better and more efficient and effective at it? So, question.
Okay, so Chris, I'm the dinosaur in the room. All of you in the front row, sorry about that.
Just don't spit
All
on
right,
them. That's all.
so let's see if I can parrot back in search manager language some of the benefits you're telling me this possibly can do besides evolution of mission, information sharing faster. Are you also saying that you're going to give me a better tool for predictive heat mapping and POAs? Is that really what you're saying?
Yeah, I mean, to be really clear where we're sitting right now, we have the core system built. So the idea that information can flow in a search management context more efficiently, that's there. A clue gets entered, shows up on a dashboard, shows up on a clue map instantaneously. There's no waiting for information. If I'm off in the room with the family member and I'm doing the missing person questionnaire, which, I've had situations that takes me 3 to 4 hours to get it through with a whole audience of people, when you're interviewing a whole family at once. As I'm making findings, everyone's not waiting for me to emerge from the living room and tell them the magic answer. They're seeing data in real time as it's getting entered. So we're already doing that. Then the next step, and where we're trying to take this system in very simple terms, is this idea that says, okay, based on that information, and then based on what historical data with AI models applied to it tell me, I'm going to recommend to you either by a heat map or by a specific suggestion of you should look over here or you should look over there. And it'll give you a graphical representation as to why. And we recognize that the typical human needs to see something visually. If we just spew out a bunch of stuff that says, you might think about all these ideas, that's very difficult to process. If I present you with a Google map and I say, here's the 3 most likely places we believe that individual is, that's much easier to process. And it's certainly much easier to process for what I call the next generation of search managers. It's not a lost art, but there's more of us retiring from search and rescue world than there are new people that really have the institutional knowledge. And remember, they're not going to gain the experience the rest of us at my age group have in the room because there's just not as many searches. cell phone technology in a lot of areas has eliminated a lot of searches. So it's going to be a longer time distance between each search, longer time to collect knowledge. And what we're trying to do is have the real-time search, collect all that data, improve the flow of information at the command post, and then give you a visual representation where you should look. I think that.
Yeah, I have a question. It was kind of answered early on. What sort of computing resources are going to be needed in the future to drive this? I mean, you're running HPC model right now. That's pretty expensive. And search and rescue teams are unable to finance anything like that whatsoever.
Yeah, so I mean, the reality is doing any technology project's expensive, right? So there's been a pretty substantial investment made into what we've done already. It's helped along. Our dollars go a very long distance when we have volunteer labor to the most part, and or very inexpensive labor. Either one works really well. So we've taken a long distance. The actual computing costs to run the core system and have that cloud environment, those are generally manageable even within a search and rescue team context, because those are consumption models. So, until you're using the system, you're not paying a lot of money to have it sitting there. Cloud computing tends to be based on what did I run, how much does it cost? You are absolutely correct. When we get into some of these, the work Charles is doing as an example, the amount of compute resource to process an AI model is super expensive. And it's one of the reasons we're presenting at the Missing Person Conference, is to try to get a government agency sponsor or some commercial sponsor that wants to willingly gift us that compute capacity, because it's beyond the scope of what we can do even in the university setting.
Go ahead.
I was just thinking about the phase of where you would use this. Obviously, you're collecting data in real time, but the predictive part, are you making the assumption that the subject is not moving so that you send resources to look there, or does it work that the subject is mobile and moving from one location to another location before you put resources on the scene?
The short answer is it's going to deal with the moving individual, because it's going to be giving you the high probability areas. We all have had those searches where, the person's down in the canyon 1 minute, but they run up the hill where it's nice and cold and to get their cell connection. And then when they get too cold and they can't get a cell connection, they run back down the hill. We certainly had one of those. She was up in our search area multiple times. Generally speaking, if I start applying temperature maps to it, it's going to suggest to me that she's probably down in the canyon most of the time because it's too cold up on the ridge. So if I overlay the weather data with the geospatial data, all of a sudden I get a different view. So it will deal with that notion of the person moving around. And it will also be able to deal with the notion of time that says the longer it goes, the more time I've given that person to get further away or get themselves in more trouble, which we very often see in the dementia searches, especially in the rural areas where they go down the drainages. They just keep moving down further and further and further. But this will predict us and tell us to go down that drainage.
So I can speak specifically about the probabilistic map approach, because that's exactly the contribution that I'm working on currently. And so time is a significant factor, both experience and the literature has shown. And our model considers time. Actually, that's part of the tabular input. Although it wasn't shown on the diagram, that would be fed in with the weather. But then from an applied perspective, as in once it's deployed and a real team is using the model, for example, you would make continual predictions. That is to say, as new information comes up, or really as however many predictions, it could constantly be predicting, right? And then time would be taken into account via constant predictions. But really at whatever granularity they see fit, whoever is using it to use the model, it will just continually update itself and thus take time into account.
Any other questions? Hang on.
apologize, I missed the first part of it, but I think I got the gist. And you said it's kind of like near real time. Could you take an input like, say, a SAR topo or something from a K9 team, and the K9 team says, hey, they're on scent and they're going through, so you get that information. So then it would then update its model, knowing that hey, we're following where we know it was, not in other places, those type of things, or even where people searched. Could it take that in almost near real time from a?
That's the intent, is to get data coming in real time, processed, analyzed, and put up on our dashboard so that the management knows, yeah, okay, oh, that's something hot, as opposed to wait for the dog team to come back to the from the field, debrief them, have somebody look at the debriefing maps, look at the debriefing forms, and you could lose minutes to hours or more. So it is as much as close to real time. That's what we're trying to do. And as Gary pointed out, like we're doing in interviews with family members, which takes upwards to 2 hours or more. That information, we can't wait for them to come out of the closet with the family. We want to get that as quickly as we can. If you got a hot piece of hot information, this system's going to recognize that, get that posted, and then we can act upon it. We're producing actionable data here at the end. That's the whole thing.
Yeah. I just want to add real quick on it. There's a ton of opportunity in that core system to recreate the clue collection process. Right now, we've implemented the paper system online. So a debrief would identify a clue. It shows up immediately in the command post. Ideally, there's a lot of opportunity with clues. It says somebody in the field, they can turn and basically take the photo, put the coordinates in, upload it into the clue log directly. Nothing stopping us from just letting people randomly put things in the clue log, and you'd be seeing those show up instantaneously. So part of what we have to do now that we have the core system implemented is, and we've done some of it already as we've gone along the way, is we now need to engineer it to take advantage of the fact that it's electronic. And so even in the clue log, we need to add in the clue log the notion that says, I can flag a high priority one, and a high priority one's the ones I want to be sorting on in the dashboard. So I'm not looking at every clue coming in, but if somebody in search management has said that's a high priority, everybody sees it simultaneously.
You're touching on what I was interested in, the searcher's interface, the ground pounder. Will they be able to input by voice, or have you gotten that far yet? Is it still going to be a manual sitting in the rain like you were doing, trying to manually enter in now on a tablet?
Yeah, well, at least they'll be on a tablet or a cell phone, not sitting there with rain pouring into their laptop keyboard that you have to have here today for the presentation. So the short answer is we did have a couple of students actually did some work with voice to text, and the voice to text technology has really improved. And so certainly you'll be able to, over time, you'll be able to basically enter text information verbally versus having to type it. So if you get to a field like the clue as an example, you're going to describe the clue. We can grab technology-wise, if you take a photo, I can get the coordinates of the photo from the metadata that's in the photo. I don't have to ask you to enter that. If you're taking a photo and sending it to me, I have the coordinates. It's in the photo. But if I want you to describe it, then we want to have the ability to say, hey, I can do it by text, and it'll convert the text into the field already.
And actually, we've done experiments with that already. I recorded radio traffic on a mock search for a couple hours, and then ran that through the computer. And it, we have our own language, right? They'll say habla la SAR, and that was part of the problem. Was I spent time with the person that was doing that to try to define, making sure what was being translated was something that is definable. So that's the hard part. But that's part of the learning data that's going to be in there, and the databases is going to have our SAR vocabularies.
Yeah, just one last simple thing I want to add there is keep in mind that the mobile devices themselves give me a lot of that text entry, that voice to text capability. We don't have to build that. So, we just need to make sure that our application can take advantage of the fact that you can today push a button and turn on your microphone and start recording. there's a couple.
I'm cutting them off. You guys have borrowed 10 minutes of Allie's time, so we're gonna carry on with the.
Thank you.
We're gonna
Thank-
carry on
thank
with
you
the
very much.
agenda. But however, there is. However, there is the panel coming up this afternoon. 2 of you with questions are on the panel conveniently, so hold those questions, and you guys will not you, but 2 of the people with questions. So I'm sure you can hold those until we get to that point. So let's have another round of applause for all these students and for Chris and his team. Yeah.